Hi everyone, the big first question, is this working on Twitch? I just got a notification saying that maybe this isn't working on Twitch. Is it? Is it working? Yeah, the thing that I'm streaming into said that they're having problems with Twitch, so let me know if this is working or not, and if not, we might have to come up with a plan. But also, hi everyone, thanks for coming. This is an Aim High Live, and this one today is about what's inside black holes these days. And yeah, it's so I'm gonna be talking about it's like a science thing, science lesson, I suppose, and I'm going to talk about mainly black holes and things that are related to that. But throw in questions whenever you want, and let's see where this goes. I'm happy for it to, yeah. But I'm interested to know people on Twitch. Let me know if this is working on Twitch. I'm going to send a message out actually before we get going. Is it working on Twitch? For those of you, oh, it is working fine on Twitch. Okay, we're all good. Right. Yeah. So thanks for coming, everyone. If you're watching on one of the Aim High platforms, then you probably know the score. If you're watching on one of mine, then go here afterwards and check out the calendar of all the things coming up. I think this is the last one for today. I don't think there's another one coming up today. Let me check. But we've got like a full cal of them next week. Yeah, this is the last one today. But yeah, we've got a full calendar of cool ones coming up next week. I'm doing quite a lot of ones on climate and ecology next week. So if you're interested in climate and ecology and you want to ask me questions about that, you can ask me a lot of questions about that because it's an area that I spend a lot of time thinking about, and I'd be happy to talk about that. But today is about what's inside a black hole. Hi Dan, hi Anne, Jasmine's back, Fatima's back, Rebecca's back. Casey's back, Kieran's back, Pumpkin Master's back. Hi everyone. Right. Okay. So we're gonna start with this because I kind of left everyone with this last time. I didn't really explain it. So yeah, today's question is what's inside black holes these days. I'm just gonna let's just highlight that question so we can keep it. So where's my pen? Here. Yeah, the first question before we get going, because I left everyone with this last time, is why do people drink tea like this? Or what kind of people drink tea like this? What's going on here? Why has that guy got his finger out? What's the deal? And oh, Jasmine's just asked me if I'll do a live on the Midnight Zone. That's to establish dominance. Live on the Midnight Zone is a great idea. Wait, I'm just going to write this down. Midnight Zone. Okay, yeah, so to establish dominance, posh people, exactly. It's like a posh people thing, but the story behind it is so interesting. And it actually relates to another one of the lives that I gave before. I don't know how many of you were there. How many of you were there when I was talking about diseases coming from animals and why it was, who remembers why it was that when the Europeans arrived in the Americas, 90% of the people there died. So yeah, for those who didn't see this live, when the Europeans arrived in the Americas, it was, I mean, obviously they had stronger military technology, so that was one of the things that made it easier for the Europeans to invade the Americas and set up colonies. But one of the big things was that after their arrival, 90% of the population died. Why did 90% of the population die when still waiting for ideas to come in on that. Although I think most of you know because I think a lot of you were on the live when I did this. But yeah, if you have like your South America especially, and when the Europeans came over, so this is the end of Spain and Portugal mainly, when they came over to the Americas, yeah, so different immune systems. So the immune systems over here had adapted to different things, and there were loads of really terrible diseases that flowed in this direction. And the bizarre thing was that almost all the diseases flowed in that direction, and the reason for that is because as we talked about before, most of the world's worst diseases come from animals because they transferred over from animals to humans. And the places in the world where there's the most interaction with animals, or the places where there was the most interaction with animals, was where there were more farms with farm animals, and that was much more the case in Europe than it was the case in South America. Because what was the only farm animal in South America before the Europeans arrived? For 1 million points. Okay, llamas. Yeah, exactly. Llamas and alpacas. I don't know if you put llamas and alpacas in the same category. They're pretty similar to one another. Anyway, yeah. So there were only llamas in South America, and so there was minimal disease transfer from them, because obviously we can get diseases from other animals. Like, we think that COVID-19 possibly came from bats, and it is possible, but the more contact humans have with animals, the more likely it is for diseases to jump. And most of the time you can hang out with ill animals and you will just never get it. It's only if you have millions of people hanging out with millions of animals that you start to get these diseases every now and then, that a human will get unlucky and it will jump to a human, or vice versa. Could be the case that a cow will get unlucky and a disease will jump in the other direction. The point is, loads of essentially unnaturally close contact with another species of animals is very dangerous, because it can result in a disease that is not too dangerous in a sheep jumping across to a human and actually being incredibly dangerous in a human. So yeah, we know that this happened in Europe. We know that the Europeans brought it over to the Americas. We know that 90%, 9 in 10 of all people died because of this. Now, anyway, I've talked about this a lot before, but the reason it relates to this guy, who is pretty posh, and I kind of want to give him a mustache, but it'll have to just be sticking out the side. The reason it relates to this guy is that whilst almost all the diseases flowed in this direction, there was one disease that flowed back. And that disease was, someone wrote it before, was syphilis. I'm just going to catch up on some of the chat. But yeah, it was syphilis that went backwards. Dan Johansson's saying cow ? But I can't remember what that's in response to. And the Pumpkin Master's saying, wasn't one of them smallpox? Yeah, so smallpox is one of the diseases that flowed in this direction and infected everyone in South America. It must have been such a terrible time. It must have been horrific. Anyway, so the one disease that went back is called syphilis. Now, I saw a comment up above from someone, I think it was from Jasmine, saying that that's a way of showing that you don't have syphilis. This is different to what I heard. I heard that I heard that with syphilis, it actually makes your joints quite stiff, and so it's harder to bend your finger, and so it's actually much easier to leave it like that. And I heard that syphilis became so rife in the French aristocracy, the posh people of France. It was so rife that actually it was almost as if you didn't have syphilis, you weren't in the aristocracy. And so people began putting their fingers up like that when they drank their tea to show, oh, my finger's too stiff to move because I have syphilis and therefore I'm part of the aristocracy, which is absolutely mad if it's true. But anyway, it's definitely to do with syphilis, and it's definitely to do with the French aristocracy. But I actually can't remember. I'm not sure which way around it is now that Jasmine said that, but I was pretty sure that it was that way around in terms of the stiffness of the joints. Anyway, right, if you're joining late, this is the Name High Live. So we will be talking today mainly about black holes, what's inside black holes these days, and we're going to crack on with that now that we've finished rambling on about syphilis and this finger thing. Can you get rid of syphilis? Yeah, I think I'm pretty sure you can. I thought it was. I'm not 100% sure, but I think it's bacterial, which means that you can get rid of it with antibiotics. But you'll have to check on that. I'm not an expert of those kinds of diseases. Right. Okay. What's this? Who recognizes this thing? What is this? And yeah, posh people are weird. Is bizarre cultures that arise. But bizarre cultures arise in like loads of different parts of society. But yeah, people with lots of money end up doing a lot of weird things. Sauron, yeah, correct. It's Toby's coming with black hole. It is a black hole. This is the first black hole that was ever properly photographed, and it's quite a close black hole to us. It's called M87. And this is a genuine photograph. So every other image of a black hole that you've ever seen will have been like a kind of artist's impression or a computer simulation or something like that. Whereas this is genuine. This is the first ever time that we've actually properly looked at it with cameras and telescopes and things. We've been like, whoa, okay, that's what it looks like. Now the thing that you'll notice is that the center is the trademark black. Why do you guys think there's light around the edge of it? Why do you think there's light around the edge? What possible reason could there be for this? Why is there light around the edge? And why is there and why isn't there a supermarket set up around here for everyone's convenience? 2 questions for you there. Why is there no supermarket on the edge of the black hole, which would be good for getting your basic goods? There's a little shopping trolley. And why is it glowing around the edge? Okay, so I'm just going to look at what people have written in the chat. So Izzy saying, is the light bending towards the gravity of the black hole? And who's that? Who's that? Athsala is saying that gravity is so strong that light bends around the event horizon. And Jasmine's saying that in response to the supermarket, it would get sucked in and die. But can a supermarket ever really die? I think they all live on in our hearts. If there was a supermarket, it wouldn't fare too well. Yes. Okay, so Oliver's talking about matter going so fast it becomes light, travelling at the speed of light. The thing about that, Oliver, is that this starts to come into this idea of relativity and like a relative view of things. So if there is matter that starts travelling so fast that it essentially becomes light, then as far as we're concerned, it is light because we're watching it from afar, and watching it from afar is going at the speed of light, and therefore it must be light. But from its own perspective, it might still be matter. It's kind of a bizarre thing. So yeah, you guys are all touching on this idea that light will spiral into a black hole. So if light goes in, then it'll start to spiral in and in and in and endlessly towards the center. Now, light is made from energy, right? And if you take energy and you localize it around a single point, so by local I mean like get it fixed to a point. If you localize light around a central point, like the center of a black hole, and it continues to go round and round the center in a tighter and tighter circle, then essentially what you've got is light energy bundled up into a tiny, tiny point. So from our perspective, looking at that from a distance, I mean, obviously we can't see it, but how do you think that behaves? What is that? I mean, obviously from its own perspective, it's light because it was light and it's carrying on, it's being light. But with relativity, we always have to think of things from both perspectives. What's it like being the light, and what's it like looking from a distance? Okay, so Eddie's saying, is it being pulled in? So yeah, the light is being pulled in, but that's only from our perspective. So from our perspective, we're looking at it and we're like, right, huge ball of gravity, a huge like gravitational center sucking stuff in. So the light is obviously going to curve around and go in. But the amazing thing is that from the light's perspective, it always thinks it's going in a straight line. So this always seems to be a straight line. It always seems to be a straight line at every single point. It never itself notices that it's curving. It's just that space and time are curving, and it's just following those things, and it happens to be moving towards the center of the black hole because space-time curves more when there's more gravity. Okay, so Rebecca's saying it's orbiting the black hole. Kieran's asking if it's super stretchy light. And Mears is saying that they think it would be fun being the light. And I agree with that. I'd love to be the light. Oh yeah, Toby's touching on something that we're about to get to as well. Okay, but the thing I was going to say is, if we, from our perspective, because the light is orbiting like that and getting really tangled up into a tiny position, it ultimately acts as matter. It acts as matter, it acts as mass. So, there's actually kind of not too much difference between a particle of like an atom of any element, and light that's so tangled up, it's essentially the same amount of energy focused in on a single point because it's inside a black hole. And so light actually contributes to the gravity of the black hole. It actually kind of makes the black hole heavier, which seems bizarre because light has no heaviness, it has no mass. But if you start to tangle it up inside the black hole, then it starts to act as if it's pretty heavy, which is pretty crazy. And yeah, Fatima, reminds you of a toilet flush. The thing that always reminds me of is, in fact, I wish I got it here, but have you ever seen? Sometimes at supermarkets, there's that thing that's it's like a funnel, and you can roll a coin in like here, and then the coin will kind of like spiral round and round the outside, down and down and down. Um, has anyone ever seen that? Because that is a great way to imagine light going into a black hole. The light, just like the coin, always thinks it's going forwards. It's always rolling forwards and forwards, but it just happens to be kind of constantly bending inwards and spiraling down and down. And black holes kind of space toilets. Well, that's that. I reckon some good stuff ends up in black holes, but then I guess some good stuff ends up in toilets when people can't take care of their good things and drop them in. Okay, Jasmine is asking what makes a gravitational field. So this is something that people have argued about for a really long period of time. But firstly, you need like a lot of localized energy. So energy all in one place. So a black hole is perfect for that because it's stored loads of mass that it's sucked in, it's stored loads of light that it's sucked in, and it's all in a tiny place. So it's all about density. Something that people get a bit confused about is they think that because Jupiter is huge compared to the Earth. So if this is Jupiter and this is the Earth, people think, oh, that's why you're heavier on Jupiter. That's why there's more gravity on Jupiter. But it's not really to do with how big something is. It's more to do with the density of that thing. It's more to do with how dense it is. So how compacted it is. Now, normally big things in space are more compacted because there's more stuff pulling them in. So yeah, Jupiter is very, very compacted. And so that's why the gravity on Jupiter is stronger. But actually, which planet, here's a good question, which planet, if you could put it in a giant glass of water, which planet would float in a giant glass of water? Which planet is so light that it would float in a giant glass of water? I wonder where we can put this. There's nowhere to put it. Run out of space. Anyway, yeah, which planet would float in a giant glass of water? What do you guys reckon? So VN's coming in with Saturn, Emerald saying Neptune, Kieran saying Neptune, Jasmine saying Uranus, Pokemon saying Saturn. It is. It's. In fact, it might be one of the others as well, but the one I know of for sure is Saturn. So Saturn is so kind of thin and non-dense that overall it's less dense than water. So Saturn could float in a glass of water theoretically. But you then have to have like a really heavy gravitational thing below to actually keep it all pulled down. It'd be complicated to set up. It's not really worth it. But theoretically, Saturn would float in water, which is pretty cool. And so that's one of the reasons why the gravity is actually quite a lot weaker on Saturn, because on Saturn it's not as dense, it's not as compacted, and so yeah, it's a lot more about gravity is about how dense something is, which is why black holes are so gravitational. Okay, right, where was I going? I was talking about spiraling light and M87. Yes, okay. What I want to talk to you about next is kind of related to what gravity is something called gravitational waves. So who here feels like they have, and it would be really good actually if you could be like honest with me, because I'd love to know, because I always thought this was communicated so badly. Who here feels that they fully understand how gravitational waves work? Who understands how gravitational waves work? Hard no. Not at all. Okay, cool. Right, I'm going to explain to you guys how gravitational waves work because I always found it really annoying how badly it was explained, and it's really not that complicated. Um, right, here we go. What I'm going to do is instead of using the way that you can detect them is by looking at like really gravitational systems in our space, like black holes and big stars and stuff like that. Ultimately, all it is this. What it's saying is that if we are the Earth here and this is the sun, then the sun is obviously gravitationally attracting us towards it, right? Now, if the sun just suddenly disappeared, like that, then would we suddenly, at that same instant, would we suddenly fire off in a different direction, just like letting go of a roundabout and kind of being thrown off it? Would that happen suddenly, or would something else happen? What do you guys think? Um, and oh, hi Midden, welcome. Us, don't worry about being late. We are. Oh, you're talking about the black hole information paradox. We might have time for that. I'm going to add it to the list of things. At the moment, we're just talking about how do gravitational waves work, and then we've got some other things to do. And if we get to information paradox, I'll do that. But I can always add it to another live because the whole black holes topic is bloody great and probably shouldn't try to squeeze it all into one. Okay, so yeah, there's some quite good comments going on. It would take 8 minutes from Fatima and Midone as well. And Izzy is saying, would we go in a straight line? And would inertia keep us going? So yeah, exactly. So we'd still have this inertia. We'd still carry on going, but instead of continuing our orbit around the sun, we'd just carry on in a perfectly straight line off out into deep space. But the key thing is, it would take 8 minutes or 8 minutes 20 seconds or whatever it is for us to start doing that, because gravity does not travel instantly, it travels at the speed of light. Now, if the sun kept disappearing and reappearing and disappearing and reappearing over and over again, then what you would get is a wave of gravity sent towards us, or pulling us towards it. I mean, yeah, it doesn't make sense to talk about it traveling in a direction, but it's easier to think about it that way for waves. But what you would get is the Earth would be attracted to the sun, and then it would stop, and then we'd be attracted again, and then it would stop, and then it would be attracted again. So we'd kind of move in this, like, continuing the orbit, suddenly moving just in a straight line, continuing the orbit, suddenly moving just in a straight line, and we gradually get further and further away from the sun if it kept disappearing and reappearing. So that's kind of the idea of the waves. The waves exist because gravity doesn't travel instantly. So it's kind of like a sound wave. It's like if you could turn gravity on and off, then you would receive it, and then you wouldn't receive it, and then you receive it, and you wouldn't receive it. Does that make sense? Anyway, I'm just gonna think there's been a couple more comments. So Clemens is saying, does it work a bit like light? Just takes some time to get to our planet, and that's exactly it. Yeah, that's what I'm thinking. And VN is saying we'd probably gravitate towards other planets. We might, but actually we're mostly really far away from a lot of the other planets, and most of them wouldn't have too much of a gravitational effect on us because the sun absolutely dominates gravity in our solar system. And we could crash into another planet, but it'd be very unlikely because the planets are... It would be kind of like if you and a friend both take like a frozen pea and you're both sat on other sides of the kitchen table and you try and throw them at the same time to hit one another. Like, you could throw thousands and thousands of peas before you get an actual impact because the planets are actually really small. Anyway, so gravitational waves, the key experiment that they look for, because obviously there's nothing in space where things disappear and reappear. So instead, in order to prove that they existed, what they do is they find these systems called binary stars. So, or a binary black hole, and that means that you've got two stars, which, sorry, I'm representing them with the Queen, I hope that's okay. It's because when I first explained it, this was one of my first ever videos that I made online, I used queens to represent it. I just thought, for tradition's sake, I just used the same thing. So yeah, you've got... So if you've got these two stars, if they're in a binary system, then what that means is they kind of both orbit around one another like this. So they're both spinning around this central point here, right? Now, the way that I explained this using queens before is I just took like a planet over here, and and I just asked, and I think if you just imagine that each of the queens is sending you like an old-fashioned summons letter, like come see the queen. That's kind of like gravity, right? So they both send letters in this position, and both the letters arrive at exactly the same time, right? So you feel the effect of both of them simultaneously. Okay, now, in fact, I'm going to get rid of the outlines because they're going to be complicated. So yeah, sorry, they're both orbiting around this point, and your planet is here. Now, when they both send letters from here, you get them both at the same time. Now, if you flash forward a few moments in time, this one is going to be here, and this one is going to be here, right? So, and then when they both send their summons letters, you're going to get this one first, and then you're going to get this one on a much larger time delay because it's further away, right? And so you'll get a different gravitational signal. And then when they move into these positions again, they'll send their letters at the same time, and you'll receive both the letters at the same time. And so then you'll get a different gravitational signal. So it's like, at first you receive like the double gravity, and then you receive one's gravity and then the other's gravity, and then you receive a double again, and then you receive one and then the other. And so this effect gives you a slight waviness in the gravity that's being received at that planet, and that ultimately is what they look for when they look for gravitational waves. Although it's hard to see it with stars, normally they use really, really dense black holes that they've found that are spinning around one another, and usually these systems don't last very long, which is why they try and find these events in the night sky to continually gather more data on how these gravitational waves seem to appear. They just find anything that's super massive and about to collide with one another and spinning really fast, because then they can record the info. And the way they do this is so cool, and oh my god, I'm almost out of time, so I'm just going to crack on to the next bit. Right. Should I will do, okay, Midnight Zone, and I might do one on LIGO, how to measure gravity waves, because that'd be a cool live to do. Would people like to see a live later on how we measure gravitational waves? Let me know if you would. And I am going to just catch up on bits of chat quickly. And Emerald's going to try throwing peas. Cool, great plan. It's so hard. It's so hard. And Clemens is asking, will the moon still be around if we lose the sun? And yes, you're right, the moon would stick with us. That would just crack on with us into deep space, being our final companion into the mysterious void. And Mira is saying we could see a Jupiter orbiting around a no longer existing sun. Well, Jupiter would also stop orbiting the sun if the sun disappeared. And Toby's asking if I'm doing the same live tomorrow as 7 Australians. Toby, I know it's getting late, but I think this live has been, the redo of this one has been moved to sometime next week, because I'm not doing them tomorrow because it's Saturday, and I just want to hang with my dog. So right, what am I doing next? Okay, there's quite a lot to get through. Oh, Miz is saying on the calendar, it's saying Tuesday. Toby, I'm going to run this one again on Tuesday. So yeah, come along then. Okay, so what's right? Satellite. Why am I doing this? Oh, okay. I was going to talk to you about how satellites work, but in fact, I think I'm going to skip a bit of satellites so that we can fit this into the time, and I'm just going to crack straight onto this graph. Ooh, where's the graph gone? Oh, I know what's happened. It's because this thing is so huge. Right, okay. So yeah, has anyone ever seen this graph before? See you then, Toby. Farewell, good night. Everyone say good night to Toby. So right, this graph here so it looks a bit complicated. I'm just going to talk you through what each bit means. So on this axis here is the let's pop that. Where could we put that? Put that there. Yeah, on this axis here is distance from the center of the Earth. So this is the distance from the center of the Earth. So when you get to this point here, which is about like 6,000 or so kilometers, that is the Earth's surface. So all along this line is the Earth's surface. Earth's surface. And obviously here is at the core of the Earth. And then if you go up to like just below 30,000 kilometers from the center of the Earth, that's how far away GPS's orbit. So actually, maybe it'd be nicer for people if I drew in a big picture of the Earth so you can see. In fact, no, it'd be better if it's this size, wouldn't it? So let's just draw the old Earth in. So there you go. There's the Earth. And here's the center of the Earth, and here's the surface of the Earth. And then this is getting to a GPS orbit, and then this is going to a geosync orbit, which is another kind of satellite orbit. The unlabeled axes were giving me anxiety. Okay, so I'm just going to label them up. So yeah, this is the distance from the center of the Earth, which is in kilometers. Now this axis here is quite a weird one, but this axis here is the picoseconds. So that is times 10 to the minus 12, I think. Wait, milli, micro, nano, pico. Yeah, 10 to the minus 12. So that's 1 second divided by a 1 with 12 zeros after it. So this is picoseconds gained per second on Earth. Now, I know this seems like a weird thing, so I'm going to explain to you what it means. But the reason why I want to talk to you about this is because it's really crucial for understanding what goes on near a black hole. And so, yes, first I want to talk to you about this curve here. So we're just looking at the green one, ignore everything else. Now, what happens if you go in outer space? What happens to time if you go close to something that's really, really gravitational? So if you go close to a black hole, or if you go close to a planet or close to a star, what happens? What happens if you go really close to something highly gravitational? So I'm going to label this green one as the gravity effect. So it warps, it slows down, it decreases, it slows. Okay, great answers coming in. So yes, if you go close to the surface of a planet, or you go close to a black hole or something in space, then time slows down. So that is all of this section here. The deeper inside the Earth you go, the more that time slows down. Now, on the other side, the further away from the Earth that you go, the more that time speeds up. Time runs faster. So for every second that goes by on Earth, if you're in a geosync orbit, so if you're this far away, then you will get a second plus 500, like almost 600 picoseconds. Now, I know that's quite small. You get, it's 0.6 of a nanosecond, but every single second that goes by, you also get 0.6 of a nanosecond. So if you're hanging out up here, you will age, what do people think? Do you think you'll age faster or slower if you're hanging out here? If you hang out here, do you age faster or slower? Okay, so Jasmine saying faster, Kieran saying faster, Rebecca saying faster. Great answers. Yeah, exactly. So the further away from the center, from the Earth you are, you're further away from gravity, so time goes faster and you age faster. So up here, you're aging faster. Age faster. Okay, so on the other side, this red line, does anyone know what this red line is about? In fact, I'll just start explaining what the red line is. So the red line is a consequence of speed. So yes, if you're near something that's very, very heavy, then time will slow down. But also, if you speed up, then time will slow down as well. So you might have heard that thing where if you travel close to the speed of light around the galaxy for a while, and then you come back to Earth, then everyone might be much, much older than you. And so all of these satellites that are orbiting the Earth, they're all going at quite a high speed. And generally, the closer to Earth they are, the faster they go. So if you're close to the Earth as a satellite, then you have to go faster. So GPS satellites orbit faster than geosync satellites, and so GPS satellites actually have time going slower, so that means that they age slower as well. So you got to take both of these things into account. The fact that because of gravity, things in orbit are aging faster, but because of their speed, they're aging slower. And so that takes us to this line here, which is both of them combined. So both of them combined, you can see that when you're in orbit around in like a satellite, time will generally go faster. So you will age faster if you're in orbit. So if you are on the International Space Station, then your time will go. In fact, the International Space Station is weird. I feel like the International Space Station might be going so fast that you might age slower. I can't remember, but I feel like something weird's going on there. But still, on most satellites going around the Earth, you will age faster if you're hanging out on them. And Kieran's asking, would our actual bodies age faster biologically speaking? And the answer is yes. But the thing is, it's not that you would feel like you're aging faster. It's that you would literally experience more time. So your clock would literally start going out of sync with the clock on Earth. Like if you spent long enough up there, you could have been keeping an absolutely perfect calendar, and you would know that 150 days have gone by exactly. Whereas on Earth, they might have only had about 149 and a half days. And you would have literally experienced half a day more time, and so it's not that you suddenly start aging faster. It's that you just experience more time. Time distorts in this way. Anyway, right. I feel like there's so many extra things that I want to get into in this because this is such an interesting topic, and I'll start throwing the ideas into other ones that I do about relativity in space and black holes. But I just want to at least tell you what's inside a black hole these days, at least to some extent. And so here to tell you is this goose. I hear there's a great video game that came out like maybe a couple of years ago now called the Unnamed Goose Game, where you just like, or maybe it was a year ago, where you're just a goose and you just go around making trouble. Sounds great to me. I'm well up for that. Anyway, the goose is so calming. I love geese. I love their flight and formation. Anyway, so inside a black hole, what happens to the speed at which time is progressing? What happens to time inside a black hole? Inside a black hole. The Oscar's wanting tensors and geodesics and Riemannian geometry, mate. We can do that, but I feel like that's not the right vibe. We could. Monkey Man's just asking, didn't they test this with planes and 2 exact clocks, and the one on the plane for 24 hours was like 1 microsecond behind or something? So yes, so there have been various. The key thing I was going to talk to you about was GPS satellites, because GPS satellites have to keep a super accurate clock in order to work, and the clock always ends up getting slowly out of sync because obviously the time it experiences is different, and so GPS satellites are constantly having their clocks updated to get them back in sync because time keeps distorting for them. And yeah, Oliver's exactly right. And Oliver's exactly right. So inside a black hole, the time goes extremely slowly. Extreme time slowdown. And so, in terms of what's going on inside a black hole, probably not very much going on because not much time is really passing, so it's barely worth even talking about. That's a good way to get out of telling you any huge amount of detail about what's inside a black hole yet. Although the inside of a black hole is very, very interesting when you start to think of it from a relativity point of view, because you have to consider what it would be like to be on the inside and what it would be like to be on the outside. And a lot of ideas say, well, because a black hole is super, super tiny, concentrated matter, then as you get close to it, obviously some parts of your body will be closer than others, and they'll experience such a huge amount of gravity that they'll be spaghettified as they're pulled in before you. So there are ideas like that, but then there are also ideas that consider the distortion of time in a different way, that make it seem like actually just plunging into a black hole would just be a like an endless fall, that you would never reach the end of, because time would continue to distort as you travel inwards. But anyway, we are black holes actually holes? Asks Emerald. And no, not really. They're more just like incredibly concentrated parts of matter where the normal physics of outer space starts to act very differently and very weirdly. And they're kind of really beautiful. And actually, when you start getting into the ideas about entropy and disorder, it starts to appear as if you could maybe create models where potentially we're already inside a black hole and we just don't even know about it. Maybe the whole universe is a black hole relative to the outside of the universe, but then what's even outside the universe? And for that, you might have been on to the other one that I did about that. Anyway, there's so much more to say about black holes. It's 43 past, and I'm going to stop now. But thank you so much for coming to this one. Do tell your friends about next week. There's, oh my god, I saw there's someone who's doing, so Phil is coming on to do a poetry one next week. I think it's on Tuesday. I think it's 11 a.m. UK time, so that's like 8 p.m. Australian time. It is, I saw like the practice run of it before. It's so good. Like, as someone who's always been obsessed with like the more sciencey end and the mathsy end, like that is unbelievable. It's going to be great. And then you've got amazing ones coming up from Nish and Hannah next week as well. Check out the timetable on what's coming up next week. Thanks all for coming. Do tell your friends and family about Aim High, and that we're giving out these free lessons about cool things to entertain people during the COVID pandemic. We will also start doing some like more syllabus school ones, because these ones relate to school ideas, and I think they help with bits of syllabus stuff sometimes. But we'll also start doing ones that are a bit more related as well. Let us know actually if that's something you want, if that's something you're interested in, or if you actually way prefer them like this, or if you'd quite like a balance. That would be really good to know. And yeah, thanks so much for coming. Do follow the social media if you haven't already. It's mainly just Instagram, to be honest, which is Aim High Live. And have a lovely weekend, one and all. And I'm just going to finish writing live. Thanks, Izzy. It's dog time. It is dog time. Farewell.